today's seminar, we're very happy to have Stefano Antonini, who will tell us about cosmology from random entanglement. Thank you very much.
Thank you very much. Hello everyone, it's very nice to finally be here. I'm looking forward to join the group. This is really exciting. So today we were talking about some work with Martin Saceda, who's a postdoc at Berkeley, and Brian Swingle, who's my former advisor at Berkeley. So I'll follow just example from last week. So I would prepare that very imperfect talk as well, except that I needed no slides because I can't really represent the word as well as Jeff. So I just decided to not give it that way. So the plan of the talk is to first give an overview and the motivation for why this kind of work would be interesting. And then I'll go through the full setup that we have and the dual boundary theory. And once we set up this playground, we can talk about exactly how the whole theory is encoded in the dual setup, and the dual boundary theories and the dual CFT. And then, if I have time at the end, I will talk a little bit about that fundamental model of our story that gives us a little bit more control over it, and so we can try and understand some properties more directly. So, I figure this is the second seminar, so I should give my one-slide review of the CFT correspondence that just tells us that the quantum gravity theory in an asymptotically ADS spacetime is dual, meaning it's completely equivalent to a d-dimensional CFT, so with one dimension less, which lives at the asymptotic boundary of this spacetime. So this CFT is a very nice theory in the sense that it tells us a lot of very interesting things about the relationship between quantum gravity and quantum information, relates geometry to the quantum information observables in the dual boundary. So it really told us a lot of things in the last couple of decades. But one problem with it is that it doesn't naturally, at least, describe cosmology. I will make a little bit more precise what I mean by that. So, any quantum theory that aims at describing physics in our universe must, of course, be able to describe cosmology. And that's just because we live in a cosmological universe, so if we're going to capture whatever goes on in our universe, clearly cosmology must be embedded in this quantum gravity setup. Now, there are many reasons why it's very complicated. I don't pretend to give here a full list of them. The only thing I want to point out is a few intuitive reasons why it's complicated. In particular, if you want to describe a realistic cosmology, then our cosmology, at least in the most simple models, let's say, have a positive cosmological constant that explains the accelerated expansion of our universe. But in a CFT, we have quantum gravity with a negative cosmological constant. So it seems like there are two quite different kind of spacetimes. Again, there is another difference, which a FRW universe, like the ones that describe the homogeneous and isotropic universe that we live in, at least in first approximation, are generally homogeneously filled with matter, and so we have matter aggregation and we have a lot of stuff everywhere. Whereas in asymptotic ADS spacetimes, as you go away towards the asymptotic boundary, the only component of the stress tensor that matters is really the cosmological constant. So again, one big difference, and the third one, which is really a consequence of the previous one, but I just wanted to point it out clearly. If you take an FRW universe and you try, and even you put a negative cosmological constant in it, which makes it into a big bang branch universe, you still never have an asymptotic boundary, which tells you that you don't really have a good place where to place your dual CFT in the standard ADS CFT setups. So these are a bunch of reasons why cosmology is not very easy to describe. And the reason why I think that describing cosmology holographically should really be a central problem in the field. And I think many people are in fact working on it. And that's why I, again, don't want to give a full review of all the different setups. Just want to give an idea of what people are working on right now in the past few years. So there are different attempts to describe cosmology holographically. I would say one of the most studied is the Sweeter holography, because our universe, at least late times, is equivalent to the zero universe, meaning that a positive cosmological constant, which is dominant, and so it's basically like a de Sitter spacetime. So if you want to describe these dynamics of our universe, at least the late times, describing de Sitter holographically is a very good, at least first step. The problem with de Sitter holography again is that we don't have an asymptotic boundary. It's not very clear how to define the dual theory, so it kind of requires a new holographic framework, which is not completely different, but quite different from ADS-CFT. Which is quite different from ADS-CFT. And then we have another approach, let's say more phenomenological, holographic cosmology, introduced about a decade ago by Alexander and Skandaris, and then other people worked on it. In this case, the approach is more hands-on. You try to compute directly, basically, cosmological correlators, relate them to a domain-wall space-time binary continuation, and then try and study the dual theory using the dual of this domain-wall space-time. The problem with this is that generally the theory dual to the cosmology has complex parameters, so it's not really clear if the dual theory is well-defined, if you have full control over it, if it's really a well-defined QFT.
Where does the dual QFT live?
Yeah, that's so the idea is that you have this cosmology, you continue to domain wall space-time, kind of a wormhole. Then you have a dual theory, which lives at the asymptotic boundaries of this wormhole, and then you just by hand analytically continue the parameters of the QFT if you want to compute the observables in the cosmology instead of in this domain wormhole. So yeah, it's not very clear where is the dual QFT, and it's not even very clear if it's well defined.
Is DS-CFT an example of this?
I don't think it's the same kind of point of view. I think in DS-CFT, frequently people try to put the cosmology somewhere on the horizon, or maybe using TT bar and finding in some horizon.
I was thinking about putting it at the future steps.
Yeah, I don't think it's the same. It's the same approach though. It's quite different. You have a negative lambda domain wall space-time that you can already continue some positive lambda cosmology. Another interesting approach, I think, is the so-called brain world approach. The idea of this is roughly our universe is a hypersurface embedded in a higher dimensional space-time. This higher dimensional space-time can be ADS, and so you can have a dual description of the whole space-time, including our universe. Again, there are drawbacks. You generate a negative lambda, or at best positive lambda if you fine-tune it, and you can have a 4D effective description of gravity in this universe only for a limited amount of time, not for the whole evolution. And finally, there is
Stefano, but that's sort of like reverse holography, right? I mean, you're putting the cosmology in a place that normally is boundary and there's a ball.
Sorry, what was that?
I'm trying to understand how brain world cosmologies fit into the idea of describing cosmology holographically, meaning by a non-gravitational theory in one lower dimension.
Right, yeah.
If the cosmology is a brain world, then the alternative description that we have to it has one more dimension, right?
It has the same amount of dimension in general. Say that you take a 4D brain but in a 5D idea space-time.
Yeah.
And then you have a 4D description of the full 5-dimensional idea space-time, including the brain. If you think of the simplified version is the West Coast model, say, where
you're wanting the brain to be the cosmology, right?
Yeah.
But still describe a non-gravitational theory. That's the idea.
Which non-gravitational?
It's if you think of the West Coast model, you would have a 2-dimensional ADS with an end of the world brain, where the cosmology is the end of the world brain, and then the dual description is JT gravity. Is okay.
You have ADS space and any brand.
Yeah, I understand what you mean, but
the holographic description is of the full higher dimensional space-time, including the brain.
yeah. I think the problem with these kinds of descriptions is that they don't allow you to ask. Suppose that there's a black hole that evaporates in the brain, and you would like to argue
So you consider that.
I mean, it's not clear to me how you would in ADS-CFT CFT, right? In principle, I know how to extract the S matrix for the formation and evaporation of a small black hole from the CFT. Not, I don't think we would know how to do that here, but maybe that's a.
I think it's not really a focus of those, so maybe we can talk about it later. But the idea in these cases is that the brain in most of these kind of negative lambda brain words embedded in black hole spacetimes lives behind the horizon of a black hole. So you can.
You're referring to Cartesian and Randolph here, right? So you have in mind a brain which intrinsically has a negative cosmological constant.
Right. Yes.
So then it's not a cosmology, right?
Well, if from the point of view, an observer living in the brain will see a big bang crunch cosmology emerging and falling into. Well, it depends on the setup you're studying. I mentioned here Cartesian Randolph to.
Well,
it's an syndrome for
you don't have any control at all. You need the brain to have an asymptotic boundary where it then couples to a CFT, to a BCFT.
No.
Right?
What I'm thinking, in the Euclidean picture, yes.
Yeah.
In the Lorentzian picture, you have a double-sided black hole with a brain behind the horizon of the black hole falling into the future singularity and emerging from the past singularity. And that is a big bang, big crunch cosmology.
That's like Upser's setup.
It's also Marx and company setup, and so that was one, and the last one I wanted to mention is again an approach that we studied with Brian and Mark and a few other people, Mark's students, and this is based on the idea of Maldacena amounts, that if you take a symmetric Big Bang Big Crunch cosmology that analytically continues the Euclidean wormhole, which is asymptotic ADS. And so you could hope to define the dual theory in terms of a CFT living on the two asymptotic boundary of these Euclidean ADS.
I'm really sorry to keep you on this point, but I still don't understand which setups you have in mind. Because
for brainward or for
the previous point.
Okay.
You mentioned lambda less than or equal to 0, but if you're talking about a cosmology with a big bang and a big crunch, then we can embed that into an ADS setting without requiring that lambda in the cosmology less than 0.
Right. The setups I have in mind, just to be clear, is set up where you have in the Lorentzian setup, you have an ADS black hole, say 5 dimensions. You have an end of the world brain behind the rest of the black hole. And so you have a brain which expands and contracts. The future past singularity corresponds to the Big Crunch and Big Bang. It's then symmetric, and the full holographic description is here.
Yeah, but that brain doesn't have to have a brain cosmological constant that's negative, right?
From a point of if you write down the equations here for the brain, what you get is that you have let's see, it's the effective 4-dimensional cosmological constant given by the tension of the brain minus 1 over LES in 5 dimensions. And this quantity is negative, unless you have an overcritical brain. Generally, when you're defining...
But you can. I mean, you can make presenter to anything you want.
Right, but then the Euclidean state that you prepare will not be well defined, I think, for the supercritical brain. That's generally what people call critical tension.
Well, as a
like in the boundary state, there's a boundary entropy that goes like log G, and
when I write down an action for the theory, for the Ball theory, I can choose the tension of this brain anything.
From the good point of view, yes, but then when you use a DSP CFT to match the tension to the boundary entropy diverges for T equals 1 over LHS. So you cannot take it larger than that, or the dual set is not 1.
And the spatial topology of this is of the brain is totally.
It is S. That's right. At least that's the model we studied. I think it can be generalized to other cases.
So in one way it is 5 process 5. If I have a critical deep brain, and then it's going to be stationary at some value C in
you get basically the next
in the quadric coordinates, right? But if I take that same critical deep brain and I make it into a sphere, a would have thought that it's not going to be stationary. I'm a little confused by that.
I'm not 100% sure about that.
In other words, the curvature contributes to the evolution of the cosmology. And so it can't just depend on the tangent and the HEP-QIS.
In this setup where everything is very symmetric, you can just...
It depends where you put the brain, right? You still have a choice of where you want to put the brain in differential conditions, right?
not if you have it full state. You need to have a tangent symmetric Euclidean integral, and once you fix the tension of the brain...
Are you going to discuss that?
What?
Are you going to discuss that in more detail?
No, because the talk is definitely not about that. I was just mentioning more. But I'd be happy to discuss it more. So, yeah, okay, maybe let me just go quickly here and just say that there is a different approach where you can relate a cosmology to a Euclidean wormhole in the DS and then define this world theory on the asymptotic boundaries of this Euclidean wormhole. This is just, I just want to give a very quick overview about what are possible approaches to cosmology that have been studied so far. What I want to do here is something possibly much simpler than that, which is try and give up the requirement to describe a realistic cosmology, so don't put a negative positive cosmological constant. We just want to try and understand how to encode a big cosmological universe into world safety. And this is already pretty complicated. So we will see that the cosmologies we have are again negative lambda, they're big bang crush cosmologies, and they have complex spatial slices, and they are inhomogeneous. So they're definitely not our universe, but they are a disconnected universe that we then study how to encode into the dual CFT, hoping to learn some general lesson.
What's your definition of a cosmological universe?
Yeah, I'm defining a cosmological universe as a closed universe without an asymptotic boundary that has a singularity, at least a singularity in the past or possibly in the future.
It has to be spatially closed.
Not necessarily spatially closed, but it doesn't have some kind of asymptotic boundary like HEP-QIS. In our specific case that we study, it is spatially closed, and I'll show in a second. Like we study a very specific setup that allows us to have much more control. The advantages of studying this model is that we can actually define the cosmological state using a Euclidean path integral, which is what people generally do in a DSFT, in the Southern quantum approximation. Another advantage is that there is a very well understood dual description, like we know what's the dual state in that case, and also in some detail the properties of the boundary map encoding this cosmological universe into the dual CFT. Clearly, this is not completely satisfactory from a cosmology point of view, in the sense that we want to describe a realistic cosmology in principle, but we can hope that this kind of construction at least teach us some lesson on how you should expect a cosmological universe to be embedded in encoding the dual CFT. And on the other hand, in general, it could give you some lesson, could teach you some lesson about how, in general, disconnected patches of spacetimes are encoded in a dual CFT if they are in a CFT set. And this could be interesting in general grounds also beyond cosmology. Okay, so before diving into the specific setup, I just want to give an overview of the results. So what we found is that we have this whole spacetime given by a cosmology. This cosmology is entangled to two additional idea spacetimes, which are disconnected from it. And the whole thing is dual to what is called the partially entangled thermal state, which for practical purposes is very similar to the term of a double state of holographic CFTs. Now, if the bulk entanglement is enough, then there is an island formula for this story, which tells you that the cosmology is encoded either in the left or in the right CFT, and it's encoded in a very similar way as the interior of a black hole is encoded in the radiation and the Hawking radiation at the late stages of the evaporation. The third result is that the map that encodes this cosmology into the dual boundary theory is non-isometric. And this is a pretty interesting fact that now is becoming more and more studied in the DSFT literature because it arises again in black hole evaporation, and it also raises some questions about the relationship between the experience of a bulk observer and what a CFD observer can prove. And I will also mention about whether or not the kernel of this map is trivial, which is, I think, something that sometimes is not completely clarified in the literature, but I think it could be an interesting point. Fourth, there is an explicit state-dependent reconstruction for this kind of cosmologies, meaning that if you act with an operator in the cosmology and you want to figure out how to reconstruct an operator from the boundary, you can do that, but you have to do it depending on a specific state you're acting on. And this is, again, something closely related to non-isometry, closely related to the black hole information problem, and so it's pretty nice that we find it in this setup and we can actually study it in some detail. And finally, there is a non-isometric to nearly isometric transition. This means that states in the book are encoded nearly isometrically in the state in the boundary. So the inner products between both states is almost preserved as long as you have enough entropy in the bulk. If the entropy is too small, then the map will be higher than isometric. And this can be shown using a tensor method toy model, but it's supposed to be, it's believed to be true in general. Okay, so this is just the overview. Let me delve a little bit into what the actual setup is. So this is the playground that we will have. This is the bulk space-time that we construct. In the bottom half here, I depicted the Euclidean sector. So the Euclidean subtle of the Euclidean gravitational path theta that prepares the state at this time of French symmetry slice. And then I include on the top the Lorentzian evolution of the state. So let's unpack it a little bit. Let's start from this Euclidean geometry. The simplest way I have to think about it is to take two thermophile double states of two CFDs at low temperatures, so below the Hawking phase transition. These will prepare the state of 4 ADSs and tangle the pairs. Then if you take these two Euclidean geometries and then you glue them together, and you glue them together along a spherically symmetric dash shell. So we take this to be a shell of matter, a pressureless matter, and then you can write down the adjunction conditions for this gluing that gives you this equation of motion for the shell. So the idea is that you just have spherically symmetric dust that you use to glue together two thermal linear spacetimes. Now, in this way, you build a solution of Einstein's equation. This is a saddle of a gravitational path integral, and then it prepares a state for all fields in geometry at this time for French symmetric slice. So what's the state at the time of French symmetric slice? Well, geometrically, you have an initial slide for an linear spacetime and another initial slide for another linear spacetime, and then you have two. This I just want to make sure this is clear. This is the R equals 0. So here you have a patch of ADS cut off a large radius and glued to another patch of ADS cut off at the same large radius, which is the radius of the shell. But that's what you get at the time of symmetric slice, and then there are Boole fields in this setup. Where Boole fields will be, and I'll comment on that in a second, mostly entangled between ADS left and cosmology left, and between ADS right and cosmology right, but not between the right and left systems.
Is this blue slice a time symmetric slice?
Yeah.
Cosmology? And why is it asymmetric between the left and right?
Yeah, that's not actually true. We have to choose whether to do a correct Euclidean sector or a correct Lorentzian sector, because these two temperatures can be different, better left and better right. But the radius at the time pressure symmetric slice is actually equal. So
it's hotter on one side of the shell than on the other.
That's correct, but the radius is the same.
Okay, but the geometry won't be exactly the same as the result, actually. I mean, since it's hotter.
Yeah, if you consider like back reaction, yes. But in first approximation, you have the same geometry, cut off at the same radius, just different gases at different temperature on the two sides. Okay, so these are temperature symmetric slice, and then you can evolve in Lorentzian time, and what you get is just ADS spacetime here and one here, and in the middle you have you can think of this as having just a partial ADS inside a dust shell. So as you're evolving in time, gravity is attractive, so the dust shell collapses, and you are inside this dust shell, and so your space shrinks. And eventually, when the dust shell shrinks to zero, you actually hit a curvature singularity, and that would be the big crunch singularity.
Do we
Now-
use anything interesting if beta L equals beta R?
Yeah, you can do that.
Because I think it gives you more control maybe, right? Because at least once you include back reaction, I mean, the radiation is going to propagate across the divided shell, right? And
Right.
it's kind of a messy. I mean, it's not even clear to me that it stays nice and clean in the Euclidean region. Probably at the level of that you're writing down.
Yeah, like at the inverse approximation, yeah. Then if you start including back reaction, of course, you have a lot of interaction between the two. You can have a very non-factorized state in the ball. You can have a lot of.
Yeah, but if they're the same temperature, then it's pretty easy.
And the same temperature, yes, but also different temperature, I think, which is important to not have the exact same temperature. Actually, it's not that important in the sense that you can. I'll get back in a second. It would be. I will actually in 2 slides I have commented on that. But yeah, so you get a singularity in the future, and of course this is time refraction symmetric, so you can just evolve it backwards in time. You would get a past singularity as well. Yeah.
So here it is the philosophy that you really care about having a boundary preparation of this state.
Yeah, you want to have like a well-defined CFT pathing throughout what you
I see.
because you want to really know what the dual state. At least in this setup, you really know what the dual state is. It's pretty straightforward. It's the next slide.
Yeah,
Sorry.
yeah, no, I get it. Yeah. So, yeah, there's it's very easy to come up with like just a Lorentzian situation where you have ADS and it's coupled to whatever cosmology you want with that nice in the entanglement waves. But I guess the advantage here is you have
You have a very
Yeah,
clear
preparation.
Euclidean preparation that actually you can use to define a liquid boundary map. Okay, this is the dual state. Since Harvey was talking about this, the dual state can be understood pretty simply. It's a thermophile double state of 2 CFTs, where at some point in the Euclidean preparation you insert a heavy operator. Now this heavy operator, so this is the representation in terms of the energy states. In principle, you can have different beta-Ls and beta-R, and you just insert a heavy operator somewhere in this Euclidean preparation. And this heavy operator is spherically symmetric, as we saw, and it can be understood to be a product of many different primary operators, spherically symmetrically distributed, and you want this number of operators to be large, meaning parametrically large in N. And that's because you want some non-perturbative back reaction that allows you to, instead of just having 2 pure ADS, to have this pure ADS plus this cosmology. Now, one interesting fact here is that this state has very small entanglement. You can think of it just because it's like a thermophile double state at low temperature, below the Hawking wave temperature. And so the entanglement between left and right is actually small. In principle, it's order 1, or at least it's not large. It's not order n for sure. It's parametrically small in n. And this also implies that the entanglement Boole field is small. Now, this fact could create some issues when you study the Boole boundary map. We will see a little bit of that later, but it can actually be fixed. And I will explain that in a second. Okay, so if you have any question about this Boole setup, please ask me now because we'll use it during the rest of the talk. Okay, I want to mention 2 things. The first thing is that we frequently use what we call the large mass limit. In the large mass limit, you just take the shell to be very, very heavy in ADS units. And this way, you get the trajectory, the Euclidean time elapsed by the trajectory of the shell becomes very small. So that's basically equivalent and leading the order to take 2 thermal ADS spacetimes and glue them to each other on a single point. So this guarantees that the state of Boole fields and the time refraction symmetric slice approximately factorizes between the left system, meaning left cosmology plus left ADS, and the right system in right cosmology plus right ADS. So this is useful because in this case, when this boot state factorizes, you can actually make calculations explicitly and actually compute quantities, which is what we did.
How that bulk state looks like? It's just like an R equals 0 and R equals 0, and it is pinched off or by a wall or something?
No, it's actually, you have from R equals 0 to a very, very large radius, much larger than the DS length, and then it's cut off by the last shell and glued together.
Yeah, so it's kind of biology.
Yeah.
Sorry, now, just because I would have thought that to make the mass of the dust shell bigger, you have to, you're saying that makes the dust shell want to sit further out?
Yeah, because I guess what we're trying to say is that Euclidean signature gravity is repulsive. Like right here, you actually see that the trajectory, if you just study this equation, the mass will be large.
But there should be a maximum mass, right, that you can have before it would have to be sort of beyond infinity. What is the mass as a function of the radius where you try to put it on there?
When you take the limit of the mass to go to infinity, you actually recover the quality of space time.
Oh, I'm surprised by that. I'm surprised that. Is there a formula for the mass as a function of the radius where the shell sits?
Let's see. Well, I guess here you get a function for the radius as a function of the mass, so you can invert that.
I mean, what the mass has to, what the shell has to do, right, is change sort of the sign of the extrinsic curvature as you're passing on the spatial slides as you're passing through the shell, right? And in ADS, I would have expected the extrinsic curvature not to diverge as you go through the boundary. It should just go to some constant, because it's like it's hyperbolic space.
Right.
It should go to some constant, so if you make the mass bigger than a certain critical value, there's just no good place for the shell. I would have,
That's a good question. I don't think I looked at the actual m equals m to infinity limit. What you can see here is that from this equation, if you study it, you see that actually you get a very small amount of Euclidean time equation for the.
Big R is the radius of the. Big R is what?
Big R is the radius of the shell. So you basically get f of r, where this is 1 plus r squared over r squared, that is equal to this quantity at the maximum radius, which is the divergence symmetric slice.
It should be a without limit, right?
So I think that's right, because you actually get, so what you get is, if you want to study the equation that defines the reflection symmetric position of the shell, you have to set r dot to 0, right?
Yeah.
So you get 1 plus r squared over r squared that equals to, proportional to, let's see, m squared.
Is that R the same as big R?
Sorry?
Yes,
sorry. Over, let's say, yes, 4, so this would be 3, check that's right, yeah. That is what you get, right? And so you get that actually the mass, the radius goes like the mass to the, what is it, the third?
But it's intuitively clear, right? And intuitively, if it goes the mass to the infinity of the operator, if you look at any kind of low dimension operator, it shouldn't contribute. It's a super high dimension. So it shouldn't contribute to physics. So that means, of course, in that method, you become 2 decoupled two-sided areas. So
Right.
the things should, that shell should decouple to the boundary of areas.
Yeah,
Of course, it's not connected to the second space, I don't care, it's just like a mass.
This mass is the mass of the shell as measured at infinity, right?
Yes.
I see. Yeah. So I think what I'm confused by is my argument applies sort of locally for the energy
Oh,
density of
I
the
see,
shell.
okay.
But of course, as you're pulling it out to infinity, it's like higher up in the potential of ADS. So
Right, that's the point.
yeah.
Okay.
Sorry. Thank you.
So, ML much greater than 1, L is the ADS limit.
Yeah.
Why do you want that limit? Just for simplicity?
Yeah,
Because it factorizes?
To factorize the
I
state,
see.
yeah.
Okay.
Because otherwise, when you have to do replica calculation, everything is very complicated. Because actually the pool partition function is very important here. And in this case, you can just approximate the calculation as having 2 ADSs basically, and then group them.
So actually, this is the limit you consider.
Sorry?
This is the limit you actually
Yeah, this is a limit, yeah.
Sorry, the calculation of what is on
Yeah, I'll get to that later.
Okay, and so yeah, as it's related to the operators going from 1 to order n, right? If you relax that,
Right.
so if you make it smaller number, so if you go back to the construction.
Yeah, I see what you mean.
So if you, that's, for that to be order n, you need ML to be much greater than 1. That corresponds to ML being much greater.
No, you can principally get still this regardless. And then...
It's like, why should the mass be heavy?
Just to
The
back
ADS?
it.
No, compared to the ADS.
Because you want the back reaction.
Right, so,
Well, okay, this, because you want this no particularly back reaction. But this, like to take the limit where it goes basically to infinity, that's because like you have a regime where you can have something that looks actually like this. But in this case, clearly the state is not going to be.
that ML order 1 or something, and you want it to be much greater than 1.
Yeah.
Right, okay.
Okay, so in this limit you have this factorization of the Hilbert space. And the other thing I want to mention, which actually is related to what Rafael was saying before, is that we saw that we have order 1 entanglement between cosmology and ES spacetimes in general, because we have order 1 entanglement between the two CFTs. But you can actually make this entanglement larger by taking this state, these pets that you prepared, and then just adding in the Euclidean relation path integral some additional operators that create entanglement between those. And these insertions will correspond to having insertions in the pool CFT, which can be local or local run depending on what you're inserting in the pool. Now, this is important because it means that you can treat the entanglement between the cosmology and each one of the two ADSs as a 3-parameter and see how the setup reacts to changing this entanglement. And in this case, it's related to what Rafael was saying, because otherwise, if you want to have more entanglement on one side and on the other, the only parameter you have is changing the temperature. But in this case, you can actually make the two temperatures the same and then just add more insertions on one side and create more entanglement on one side. Okay, so we have the playground. Now, the main thing I want to talk about is the photo-boundary mapping setup, and in general how this cosmology, this closed universe, is encoded into the wall at CFD. Okay, first of all, I want to mention that if you ask where is the left ADS encoded, well, really in the left CFT. Where is the right ADS encoded, really in the right CFT. Where is the cosmology encoded? That's an interesting question in the sense that it can be in the left, it can be in the right, or maybe it's in both of them in the sense that, for example, the interior of a double-sided black hole is only encoded in both CFTs at once, not in just one of the two. So one could ask this question, and if to ask this question, you can compute entanglement entropy of one of the two CFTs. Say the left, it's the same because the full state is pure.
So here it's clear that it's going to be encoded in one or the other, right? Always, because
There's no area.
there's no area. Right?
I don't think that's super clear in the sense that it's clear if you have enough entanglement, because if you have a tie situation, I'm gonna spoiler. This is what you're talking about, right? So you have the left ADS, a right ADS, some entanglement in the pool.
Well, when it's really close to the transition, then it's always.
Yeah, if it's really close to the transition, it's not clear. But the problem is that also if it's not one of those excited states, but it's instead just a path, you have order 1 entanglement. And so you don't have a really sharply defined QES in that case.
Yeah.
So, my point, so I already spoiled, so let me just say that my point here is that if you compute entanglement entropy of say the left CFT, you find out that the quantum extremal surface is certainly trivial. It's the empty set because the full ADS left is encoded in the left, and then you can just decide whether you're including in the entanglement wedge the cosmology or you're not. And that depends on whether there is more entanglement between cosmology on left or cosmology on right. So if you have more entanglement between cosmology on left than you have between cosmology on right, then the cosmology is an ion for the left. If it's the opposite is true, the cosmology is an ion for the right. And if you just don't have enough bulk entanglement, then I guess this answer is really not clear. Like it's encoded all in both sides. Okay, notice that this cosmology is an island, so it's probably encoded in a very complicated way into the dual CFT. And this complicated way, so we can expect it to be encoded in the dual CFT similarly to the interior black hole layouts in the evaporation process. So we can expect to have isometric maps, independent reconstruction, and so on. And so we went on and tried and figure out if this is actually the case. And in this setup, turns out that you can do it pretty simply. So we're interested in studying mostly the encoding of the cosmology specifically, not of the full board setup, because really ADS left and ADS right are encoded very easily isometrically, just HPLL. But the cosmology is encoded in this more complicated way. So we want to restrict the attention to a pull to boundary map that we call cosmology to boundary map, where you take, you basically fix the states outside and you just focus on on the states in the cosmology. So to do this, we try to work in a very simplified settings that gives you control, where you consider the insertions in the dual CFT of some heavy operators, and with heavy I mean not heavy enough to back react, but heavy enough to satisfy the geodesic approximation, which means if you insert an operator, that creates some particle that then propagates along the geodesic in the full geometry. Okay, given these insertions, we can consider three types of insertions. Type 1 are insertions made at some Euclidean time such that the geodesic hits the time-symmetric symmetric slice in the cosmology. Type 3 is the same thing in the AES. Type 2 are a bit more complicated, but the idea is that they create some entanglement between cosmology and AES. So, what is the effect of these insertions in the bulk? It's creating a particle in the cosmology. So you can think of them as just, from the cosmology point of view, from the bulk point of view, to just acting with some simple creation operator in the cosmology, and then corresponds to having this insertion in the Euclidean path infinitesimal. So we're interested in the cosmology specifically, so what we do is we fix some reference state, psi, which has a fixed number of type 2 and type 3 insertions, and so you have a fixed state for the two ADS, you have a fixed entanglement between ADS and cosmology, and then on top of that, you consider type 1 insertions. This means that from a bulk point of view, you take your reference state, you act on it with some local operator that creates a particle, and that defines our state. Now, these local operators can be any kind of local operators. You can create a particle with spin up and particle with spin down, and then electron and proton. And you have many of these different states. In the boundary, this corresponds to having a state in the CFT, which is defined in terms of that CFT path integral we saw. So we have just a time order product of the operator itself in the shell, the operators preparing this reference state, and then the specific operator that inserts this particle. So in this case, we have a well-defined bulk state and an operation to make it, and well-defined boundary state. And so we can ask, we can just define the bulk to boundary, the cosmology to boundary map to be the map that acts on this bulk state and gives you the boundary state apparently using this Euclidean path integral. So this gives you a way to define through that Euclidean path integral of the CFT a well-defined bulk state and a well-defined bulk to boundary map, and then you can ask whether this map is isometric or not. So in order to do that, well, one can do.
Stefano, first of all, type 1, that's when you add a particle
in the cosmology. Yeah. The idea is just we are fixing the state here, here, and entanglement, and we're just like take the cosmology, add the particle to it. That's a difference in the cosmology. That's it. That's how we define our cosmos space.
Oh, I see. Yeah, I was missing I was trying to understand why you were making that in such a different put that on different lines.
Because ADS is included.
So you want the code subspace to distinguish between all of these insertions of type 1.
Yeah.
But not, the others are fixed, we already know that.
Yeah, because the others are just particles in ADS, and we know that. Type 2 just create entanglement. That's the intuition. But that's a limited case. So let's say type 3 are kind of trivial. They are just creating a particle in ADS. You just can use HEP-QIS value out, and that's it.
But you could have varied the type 2 insertions instead of the type 1 insertions. It would have been an interesting question to study as well.
That's an interesting question. Our intuition for type 2, and this is more intuition than a proof, is that you basically have two competing geodesic, and notice that this insertion must be like a very small epsilon that goes like 1 over, I think, the mass of the operator that you insert around the beta fourth, like goes here. And if you have this kind of insertion, you have two competing geodesics, and so you can think of that as a 0, 1 plus 1, 0 state of the cosmology. And yes, so you're increasing entanglement by making these insertions.
I'm actually a little confused why you draw them so close together. I mean, like, consider a type 1 insertion, but in the other cosmology,
Yeah.
right? Let's call that operator A that does that. And let's call the operator that does the type 3 insertion on the right B.
Okay.
And let's say there are two kinds of each operator, A1 and A2 and B1 and B2.
Yeah.
I could have created an entangled state like type 2 just by acting with A1, E2 plus A2.
Something like that, yeah.
And then they'd be really far apart, these insertions. So it's not important, right?
Yeah, but
It's important that they're entangled, not that they're close together.
Okay. In this way, you're like correlating the insertions of the operators in the Euclidean.
Yeah.
But in
Well,
the
what stops me from doing that?
Our idea, like this is a debate, it's not really important, type 2, I would say, in this context, but our idea is that if you actually insert a single operator here, these are not two operators inserted, it's a single operator inserted. And you have two possible geodesic that are competing. One that ends in the cosmology and one that ends in the ADS.
Okay. That seems like a really fancy way to create entanglement, but I don't know why you would have to.
Yeah, it's
Right.
one way, yeah, I agree. That's why I say it's not important. I'm just saying that it's not really important. I think that this should be right, but yeah, I mean, it's not the only way to create entanglement, I agree. You can just insert also very, very light operators here that just. Yeah.
So for your philosophy, does it make sense to just consider the boundary map, or the boundary is just the union of left and right?
Yeah.
It's probably presumably the most straightforward thing to consider. You don't have to worry about
the
phase
yeah,
transition
yeah.
happens.
Like the same example may apply to like
Right.
generic pull to boundary map, and then if you have a well-defined Adam formula, then it will be a one-sided pull to boundary map.
Yeah, probably. So even if you have a one-sided thing, you can still consider the two-sided thing. Maybe.
Yeah, but any state in the cosmology would the map would actually be
No, the map that maps the cosmology to the union of the two boundaries could still be.
right. But if you trace out
Yeah, I think
in
it depends.
the codomain, if you trace out one of the boundaries,
yeah,
you
yeah.
can
Find the one-sided map.
Yeah.
Yeah.
But I agree.
But
you
the
can be
time
double-sided
The
if
complexity
Yeah.
will be different.
Yeah.
Yeah, but the last step will be dense.
yeah.
That's not.
But it's you can do it double-sided, one-sided.
Yeah, downside and then do the best map.
Okay, so we define this cosmology boundary map where you just have these different type 1 insertions, and all the different states that you prepare by acting with these operators in the cosmology are mapped to boundary states defined by this Euclidean integral. So to ask the question of whether or not you have an isometric map, what you need to do is take two different states in the cosmology that are orthogonal to each other. For example, you just take
So I'm confused with that expression. What's this O to B tilde?
so this is the operator inserting the shell. This is the operator preparing the reference state. So like 2 to 3 insertions, light insertions, whatever you want. And this is the operator inserting the type 1 insertion.
Oh, that's fairly complicated.
It's this basically. It's that you insert first the shell, then type 1, then type 2, then type 3. That's what it's telling you, this one. And you have to do it in the right order, of course.
And this is the states on the single boundary?
This is a state in principle in both boundaries, yes.
With both boundaries?
Yes, on both.
I He's just saying the first operator just creates the geometry.
Yeah.
The second operator just creates what's in the first bullet point,
Yeah.
which is still being held fixed in this code subspace. And the third operator is the one that is varied and generates the code
So
subspace.
two different states in this code subspace will differ
So you're just going
only by the
to
form of this.
the psi i's on the left hand side that are made this way as to approximately what we're talking about now.
Yeah.
Ah, okay, that's okay. I think I know.
And so you can take two different type 1 insertions that create two orthogonal states in the cosmology, and say you create a proton, you create an electron, the two states are orthogonal. So clearly the ground matrix in the cosmology is diagonal. Now the question one can ask is this ground matrix diagonal in the CFT? So once you take the states, you map it to the boundary, compute inner products, is it still diagonal? So you can answer this question using the Euclidean gravitational path integral. So what you do is you fix your boundary conditions, say insertion of a particle I, insertion of particle j here on an operator I and operator j here on the boundary, and then you just finish the path integral to compute the overlap. Now, if you just compute the overlap as it is, it clearly gives you the same answer because you have as the bulk. And this is because you need to connect this geodesic that carries a flavor j to a geodesic that carries a flavor I, and they don't connect to each other, so this is clearly 0. So it looks like the map is isometric. Well, no, because as usual in gravity, if you compute the square of the overlap, then the answer is non-zero, due to the presence of a different Euclidean saddle, which is a Euclidean wormhole. Now, the reason for that is because if you compute the square, you have two particle i's and two particle j's, and they can actually connect to each other in this kind of saddle. So this is a Euclidean wormhole saddle, and gives you that the square of the overlap, its contribution gives you that the square of the overlap is actually given by e to the minus relative entropy of Boole fields in the right ADS plus relative entropy of Boole fields in the left of ADS.
Just I expected the square of the overlap to involve like twice as much drawing.
This is like, I didn't know because these are twice as long. You should think of these as a full boundary and these as a full boundary, and then there's a limit overall.
Conformally.
Yeah.
Okay.
Okay.
Yeah. And so you get this answer, and notice that this is not actually decimal. Again, because these entropies are not parametrically suppressed in F, they are actually order 1. So this is small in the sense that e to the minus anything is small if anything is larger than 1, but it's not it's not parametrically small enough. Yeah.
Just to make sure I understand, the circles here have like 2 beta L and 2 beta R.
Yeah, it's like beta L here, beta R here, beta R here, beta L here. Yeah. So this is not decimal. What is this telling you? This is telling you that it's kind of strange, right? As usual, this happens often in gravitational path integral. Gravity, the idea is that if you compute an overlap, it's 0. The square of the overlap is non-zero. This is strange. The reason is that gravity does not compute the overlap in one CFT. It computes an overlap in an ensemble of two CFTs, and it takes the average over the ensemble. In this case, the ensemble is given by the shell operators, in the sense that you have the shell operator that has this macroscopic description in terms of a dash shell, but there are many different microscopic ways to create this dash shell, and that can be seen as an ensemble of different operators insertions that gives you just one macroscopic picture. So this idea, so this is telling you that of the diagonal elements of the ground matrix in the CFT are 0 on average, but are non-zero if you just take one realization. So the map is non-isometric, because the bulk EFT tells you that it's 0, then CFT tells you that it's non-zero. And it's pretty interesting, I won't go into that if you consider type 3 insertions, so the ones that create particle in the ES, you can do the same calculation, you still have the Euclidean wormhole, but you actually get a suppression factor which is very, very suppressing and gives you nearly 0 for the square of this overlap, due to like how these particles connect. And if anyone is interested, I can talk about it later, but it's just a consistency check that if you consider what you know, you actually get an isometric map. If you consider just AES.
Should we be surprised that it's not exactly zero?
Yeah, that's what I was. Is it like?
That's a good, it's like extremely small. it's not zero. Yeah, I guess that all these questions are, all these answers are approximate. Right?
But they're satisfying the geodesic approximation and still it's non-zero.
Yeah.
Because if you imagine there's some spreading of the particle itself, it puts part of it behind the horizon. But you're saying the leading order in the geodesic approximation, the answer is non-zero.
If you just use the geodesic approximation, the answer is suppressing the length of, in the ratio of the length of the geodesics, which is a very, very small number. And the point is that all these calculations are clearly approximate. So if you get something as a result that is like 10 to the minus 30, it might be zero.
Length of geodesics, as in what are?
The problem is that in this Euclidean wormhole and in the this is unnormalized and then you have a normalization factor. So you basically get for type 3, in the normalization you get a length of the geodesic which is similar to, let's say, this type 1. But in the Euclidean wormhole subgroup, the length is much longer.
But it's not like parametrically, you know. What parameter controls that?
It goes like,
You know.
let's see, it goes like, I have to check, I don't remember. I think, yeah, because you have a separation due to the gravitational action, so it is parametrically longer, yeah. And the separation design comes from the bulk instead of from the boundary. In this case, the separation comes instead from the bulk fields instead of the geometry. In this case, it comes from actually the geometry, so you have a factor around there. So it's parametrically suppressed.
The separation factor is e to minus some finite number.
It goes like e to the minus the length of the edge of the geodesic, the length of the geodesic.
So is the intuition that there is a geodesic, if you want to connect an I to a J, where I and J don't match, geodesic would have to, even though it starts on the boundary, it sort of goes behind the horizon and comes back out?
No, not really.
It's the geodesic that remains outside the whole time.
The geodesic remains, well, in the Euclidean wormhole it's not clear what's inside, what's outside.
Well, it's equal zero slice. So.
Yeah, but this is like, you're gluing together the inside and the outside and finding
Some
some
geometry,
and finding
yeah.
some new sample. So I wouldn't say it's clear what's inside or what's outside in the Euclidean wormhole.
So presumably if you sort of did the, I don't know, fixed area versions of these, it would be exactly zero maybe?
It could be, yeah.
I see.
Just to understand this point, so generally with a non-isometric map, I would expect these overlaps to depend on two things, right? One is sort of the bottleneck, like how much output do you even have, which I think is...
Which is this.
Yeah, which is this, exactly. And because that's sort of the entanglement that you have to push it through, right?
Right.
But then also the size of your code subspace, in other words, how many different psi i's you want to actually encode. Presumably that would go in here as a factor.
Right.
Is that? I mean, you can't at fixed at S2s of rho R and S2 of rho L, right? The map has to become highly non-isometric as I make the code subspace large. Right? As I increase the number of operators.
With respect, yeah, right.
So that's not visible in this.
Oh, I see.
The right hand side looks small, independent of the size of the code subspace. Let's say it's small.
Well, but I guess there is this is a bulk entropy, right? So there is that includes the notion of how many bulk fields you have.
If you could just go back for a second to the previous slide, maybe even more previous. Yeah, there. No. Yeah, exactly. Isn't the typical overlap of these the big size depend on how many different states this index capital I runs over?
Okay. Wait, I notice why would you not have just a dependence on the bottleneck for how many states you can for
remember this key quantum information result that goes into the last metric mass paper that I read. It's like, there's let's represent this with the usual picture where we have a random unitary, there's a certain number of input legs, right, and then there's some output legs, and equal number of output legs, but I project on some subset of them, right, and then I can ask, well, to what extent can the output still distinguish, some subspace on the input legs, and there's some relation which I think is actually exponential. It's not so.
Right. I think I know what you mean. I think one difference that you can see here is that if you do it with a gravitational path integral, and probably that's something I wanted to comment in a second, which is the fact that the map is non-isomeric doesn't mean that it has a non-trivial kernel. So it doesn't mean that you are not able to encode all states into the dual CFT. That's true if you work with finite dimensional Hilbert spaces. And in fact, if you limit your CFT by truncating the CFT to a macrocanonical band, which is something we did in the next slide, then you find that the rank of the ground matrix is upper bounded by the macrocanonical entropy. And that depends, it's like, if you take, again, spoiler, if you take the rank of the ground matrix in the macrocanonical ensemble by fixing some energy band, then you get you do the resolving calculation, you find that it's the minimum between the number of states that you're trying to encode and the into the macrocanonical entropy. So I think that's what you were looking for, right? But I think, that's something I actually was about to comment on, which is the fact that we have a non-isomeric map, it just means that it doesn't preserve the inner product. But I don't think that that's generically, I think that's something that sometimes maybe it's overlooked. It doesn't mean that you have a non-trivial kernel. So it might be that you can encode all your bulk orthogonal EFT states into a bunch of non-orthogonal CFT states, non-isometrically, but still without having any null states. This is possible I think this is in principle possible. I don't see why this shouldn't be, because any CFT state, if you have the full CFT, you can write it as a superposition of all energy eigenstates, unless it's a specific state, and you can have, for some energy of the state, the coefficients of the very high energy states, so the thermal tails, to be very, very small, but maybe they're different from each other. So you could have two states that are nearly parallel, but they're still linearly independent, and you can do that for all bulk different theory states.
So
I think it would be more strange the opposite than this. So I think in principle,
but that would be very different from black hole.
that would be different from black hole in the sense that in the black hole you just are looking at a fixed number of states in the dual CFT given by the vector in entropy, and you are like limiting yourself to some subset of the Hilbert space, which is equivalent, let's say in this case, to fixing some microcanonical band and just fixing an energy for the state.
So in the canonical ensemble, you'd say the same about the black hole.
Yeah, I didn't think carefully about the black hole case specifically.
Black hole case is obviously this case.
Is it?
Yeah, because volume is huge. You can think about independent bulk effective theory states beyond the area of volume.
So the CFT Hilbert space is infinite.
Yeah.
No, it's macrocanonical ensemble. You take a macrocanonical.
No, I think in
If you get a macrocanonical ensemble,
I think the question is like in the canonical ensemble.
Yeah, I'm not
Macrocanonical ensemble is still the same.
Yeah, I think so. Yeah.
The canonical is not zero.
In the microcanonical ensemble is the same.
Okay,
In the
okay.
canonical, I'm not sure.
Okay, canonical, I don't know.
But yeah, in this case, like, it seems pretty. It's actually more fine-tuned to think that there are that all these like thermal tails conspire so that you get null states rather than not. So the idea here is that if you actually are an observer in the CFT, which has infinite power, infinite control of the state, can see all energy eigenstates, you could actually be able to distinguish states in the Polk FT, even if the map is non-isometric or Polk
I don't understand that statement, because you're saying, it would require infinite fine-tuning for two states to exactly coincide after the map B.
If you have an infinite
But if they're almost coincide, then there are results that tell you that you cannot distinguish them. I mean, you can distinguish them with extremely low fidelity.
Yeah, so you need to be you need to know extreme precision, the CFT, which is non-physical.
I don't know, but I thought that's not a question of precision. It's just a fact. I mean, it's I guess maybe you have in mind a lot of copies or something.
Yeah.
You can do it with limited precision.
Yeah.
But
that's what I mean. It's not a physical. I agree that it's not a physical point of view. I'm just saying that the fact that the map is not isometric doesn't mean there's a non-trivial kernel.
We could say,
And that if you are an infinitely powerful CFT observer, you could in principle distinguish them. I think this is the case which is more physical, which is you're not an infinitely powerful CFT observer, you just have access to some energy band, and if you do that, you actually find that the rank of the grammatics in the CFT is actually upper bounded by microeconomic connection. So this is telling you that you do have states in the Polk FT which are mapped to known states, and so you do have states in the Polk FT that you cannot distinguish as a limited CFT observer.
That's the physics, but it's, you say mathematically, you have canonical ensemble. Mathematically, you have infinite number of independent states. Well, of course, it's exponentially small. Coefficient was exponentially small, but then in principle, you have an infinite power, and that at least makes sense to consider because you're now mapped to a non-gravitational system, so you can have open rule observer, which is outside the CFT system, has infinite power.
I think that's in principle right.
Yeah, it may not make much sense physically.
Physics, yeah, I agree with that. I think this is the physical statement where you do have more states in the board. Now, okay, I'm very much out of time, so let me.
so this expectation in the canonical, is this, did you test this?
No, this is an expectation.
Because
I was just pointing out that mathematically you can have a non-symmetric map.
There is
no trivial kernel.
Yeah, but I think it's good to see if it actually if it works out this way. There's this paper by some people, I think Luca and Champagne and some other people, where they talk about global symmetries, and they talk about how you can, if you have various, let's say these, you insert create one of these pets with many flavors of matter field, and you want to figure out if you can argue with the path integral that you can write down one of these flavors as a sum over other flavors.
Right.
So if you can do that beyond no state,
Yeah.
and the sort of the arguments was pretty standard. I wouldn't be surprised if somehow for pets their argument doesn't go through.
Okay, so
Suggest
their
that you
case
can.
defined.
Yeah, I mean, I don't remember if they were super hung up on microcanonical, but I doubt it. It just seemed like quite standard arguments went into that. So yeah, okay. I mean, I just wanted to make sure that this isn't something you.
No, this was just this was a comment. It was not
Okay.
a proof. Yeah. So let me just mention that, given that I just want to mention that given that Euclidean path integral for the CFT, you can define a Burke boundary map. You can define a reconstruction of Burke operators acting in the CFT using just a Euclidean path integral. And if you do that, you see that the reconstruction that you can build is clearly state dependent. That doesn't mean that there is, in principle, that there couldn't be another state independent one, but it seems pretty clear that you have an isometric map and you have something which is encoded in a very complicated way, so it's not crazy to expect that the reconstruction cannot be state dependent. And in fact, there is some work in progress with Charles, Martin, and a few other people that we're trying to make a little bit more clear the connection between non-isometry, state dependence, and really the causal structure of the Burke spacetime. This is some ongoing work, and I'd be happy to talk about it later on. But for all practical purposes, what we're saying is that state dependence and non-isometry are the same thing. At least, of course, that depends on. You have to be careful of how you define your closed subspaces, but state dependence and non-isometry are the same thing. And state dependence and non-isometry imply and are implied. This is we still didn't finish the proof yet, so it might not be true, it's a conjecture for now, imply and are implied by the presence of what we call a boundary disconnected region, meaning for practical purposes, either a disconnected space-time like this one, or the horizon of a black hole.
Why is this not a special case of the conjecture that in Python's lunch leads to?
Which conjecture, sorry?
I mean, I thought the whole non-isometric map sort of story was centered around the idea that anytime you have a Python's lunch, that the map from the lunch to the boundary is going to be non-isometric and stable. And the examples you list here seem to be special cases of that. Maybe
Yeah, so special cases of that.
I mean, anytime you have a disconnected universe, that's kind of automatically a Python's lunch.
Right. But I think in these cases you can actually show it a little bit more easily. Like the Python's conjecture, I'm not sure if it's already how clear. I think in this case you can build pretty easily some argument that tells you that this is true. If you have it behind the horizon, if you have no causal connectivity between the region, your inserted operator, and the boundary, and the global boundary. So that's the point. And then I think it's like actually showing that the isometric and state dependence is the same thing, and it's an if and only statement.
Isn't it enough that you have maybe more effective degrees of freedom in the launch and entanglement between the launch and the rest of the space? I mean, that's sort of what forces you to have non-isometric maps, right?
Yeah, I guess if you think from a tensor network model kind of point of view, I feel like that's pretty clear. I think here what you can do is try and formulate in terms of entanglement wedges and understand that if you have different entanglement wedges for different states, and that can only happen if it's behind the horizon. We're still working on this proof, but I have some idea how to show it. I'd be happy to discuss it later. This is like something else from what I was talking about today. But yeah, like we wanted also to go on and try to make a precise connection between that and the balance image conjecture, because it's like there are a bunch of scattered and not completely put together statements in the literature about like state dependence on isometry and the relationship with Python's lunches and the fact that every operator behind the horizon is state dependent reconstructed. It's like some of them are precise, some of them are some lower. It would be nice to like have a very precise statement of all these things together. So
Let's talk more about that.
Yeah. Okay, yeah, the last thing I wanted to talk about is this highly non-isometric to nearly isometric transition, and then can be studied in the tensor network model. The idea is you can build this tensor network where each of these triangles is a mere isometry. It's basically a space-time. The one here represents the two cosmological patches, and this curved edge means that we are cutting it off in some large radius, and then we are gluing them to each other along this operator insertion. And we have then the left yes, and we have some entanglement between cosmology left and cosmology right. Now, we take this operator to be Gaussian distributed. There is some argument for why that's the case. Basically, we're always considering now Euclidean rules, Euclidean path integral rules, that this operator connects only 2 by 2, and if you consider higher moments, those are suppressed. So this is a property of the Gaussian operator, and if you actually choose a Gaussian operator, you find that this tensor network gives you the right answers for example, the Anna formula. So it seems to simulate pretty well our setup. If you do the Anna calculation, rapid calculation for this story is pretty interesting, because you actually get a subtle where you contract this, when you average over the Gaussian ensemble, you actually get something that looks very much like the rapid overload that gives you the Anna.
I think that's related to what Arvind was saying. If you did this with fixed area states, I think it's literally just.
Yeah, that's right, yeah. Okay, so this represents the island, and you can use it to define. I'm out of time, so I don't want to go into many details, but you can use it to define your point-to-boundary map. As usual with tensor network, there are some bulk states, and this bulk state is on legs that live in the cosmology, legs that live in the ADS spacetimes, and you can take the Hilbert space of the cosmology to be much larger than the one of the 3DSs. And if you do that, clearly the map is non-isometric, because you have some bottleneck here, and you cannot encode more states than L times 7. So, one thing one could ask is, when are all simple cosmological states, and I will make that precise, encoded isometrically? What I mean by that is that in the black hole information story, one question that was asked was, if I have a limited bulk effective theory observer that doesn't have too much power, then can I actually tell that these states are equivalent to each other? So this is a similar question in the sense that you can define some simple cosmological state, and the simple state is defined to be prepared only using k-local gates by powerful observer, meaning that it has access to all the degrees of freedom in the cosmology, and this observer cannot live longer than the lifetime of this big bang grunge universe. So this seems like a pretty basic kind of requirement. Given the assumption you can estimate,
There's an observer in the universe, right? Or
it's an observer in the cosmology, yes.
it's probably equivalent, but I would have thought we want to ask about what states could be distinguished by an observer in the universe. But maybe that's the same question.
What we're asking is how many simple states there are, in the sense that what are the states that an observer can prepare? How many states there are that a simple observer can prepare? And then what we want to ask later is, so if you pick this number of states, what is the probability, using that Gaussian ensemble, that these states are encoded nearly isometrically?
Yeah, I'm just like, when we actually do cosmology, we might look at something like the CMB. And the things that we want to be able to discuss are different patterns in the CMB, that point to, I don't know, this other origin of structure. But what we're not capable of doing is measuring the actual state of some specific subsystem of the universe. That's much too difficult. And that's not what you're asking here, because the CMB, I couldn't prepare that, right? That's sort of already prepared for me.
Yeah, what I'm asking here is, if I am some limited observer in the book, then what is the probability that any state that I can observe is highly non-isometrically encoded? And so it means that there are like equivalent states in the book.
So maybe you want something a little bit more general than what you do here. You probably want different patterns in the CMB to be non-isometrically.
Wait, why is
Sorry, to be isometrically encoded. I said it the wrong way. Like stuff that we care about when we do cosmology, we don't want that to be lost in the map.
right?
That's
Yeah.
okay.
But yeah, also in the setup, like, not sure whether it makes sense to look at the CMB because it's like a very simplified setup. You don't really have this universe, but yeah.
Oh, sure, but at the level at which you're asking these questions, you want to define your big goals, right? I mean, that's
Yeah, but like, this is like a way to, the point is that you want to count the number of states that an observer can be able to prepare. It is.
I mean, in your model, you also don't really know what a powerful observer can do, or how do you know that?
Yeah, so you're just modeling an observer by being someone who cannot live longer than the age of the universe. I think that's pretty.
That's cool.
Yeah, and then you're just saying that it cannot act extremely or locally on the universe.
Thank you.
No, do you
Yeah, no, that's a good model for what a sensible observer might be able to do. Yeah.
Yeah, okay. And so you can estimate this number of states, and this is the result that you get, where C again is the dimensionality inverse space of the cosmology. And if you do this, then there is a well-known result that tells you that, well, I don't know if well-known, no result, that tells you that the probability that if you take just K states, the probability that they are highly non-isometrically encoded is upper bounded by this quantity. So,
Can you simplify that in some ways where like there's too many logs, exponentials, and these?
this one?
Yeah, everything.
Oh, log.
Well, that's the upshot. Yeah.
Okay, so log is 1, always. So,
Yes, that's what I would.
okay, so this is 1. So you just get log 2 to some power that doesn't matter.
Great.
So you
And
get
C is
infinite
what?
log of the dimension.
What is C?
C is the dimension of the inverse space of the cosmology. the dimension of the bulk effective field theory space, the code subspace.
So and K is what? Oh, K local.
K is the local.
So in the end, the big K is equal to the dimension of the Hilbert space, roughly? Or
So, no, the big K is the number of simple states.
yeah, what I'm trying to understand it's exponential of some number that's order 1 times the log of the dimension of the Hilbert space to some power that's also order 1.
Right.
It's very hard for me to parse what's the outcome of that, because depending on these order 1s and where they go, could be much bigger than the dimension of the Hilbert space.
Right, this is an estimate made using the fact that it's only using low K local operators.
Yeah. So is there a simplification that K is, I don't know, little c to some power or something that's the
Yeah, K is, it's basically, I would say it's e to the, let's see. Yeah, it's like c to some power.
To some
G
fraction
to
power, I
yeah,
guess.
it's like some fraction of the.
So essentially, it's just saying e to the some number times k.
What?
E to the some number times small k.
Yeah, basically, yeah.
Yeah, but that number is the log of the dimension of the Hilbert space.
Yeah,
right?
it's smaller than C.
So the point is,
Yeah,
it better not be bigger. I mean, that exponent on C better not be bigger than 1, but you're saying
and no, it's not.
some order 1 number smaller than 1, so
Yeah.
it's all at the square root.
Yeah, so it is smaller than the dimension of the Hilbert space. But yeah.
And where does the lifetime come into this?
The lifetime, yeah. So the so the lifetime in this is coming in how you estimate the hold on.
I think that, given that the radiation is thermal on each side of this thing, and,
Everything's related to C.
yeah, everything's probably related to C.
Yeah, and the lifetime comes in because you have the ratio between. You have basically when you to compute this formula, it's a long calculation, but the idea is that you take the number of states that have complexity smaller than some arbitrary number, and then you estimate the complexity using like the equivalence between complexity and time. Of course, it's just an estimate, but the equivalence between complexity and time, and then you use for the time in order to upper bound the complexity. You use the age of the universe, basically. So you want like the number of states with complexity C, and then you want C to be the largest possible complexity using only K local gates, and for an observer that only can move for some time as long as the lifetime of the universe. Okay, and so what you get here is that what this is telling you simply that if you have K states, then the probability to have a highly non-symmetric encoding is smaller than this number, when we can plug in the K here. And if you do your math, this is what you find, which is telling you that if you use this estimate for K, and we also estimated the number of bulk degrees of freedom that you have in naive bulk effective field theory, and that goes roughly like 2 to the n for each one of the 2 CFT, but to some number again. Then all these simple states are approximately symmetrically encoded if the bulk entropy in the left plus the one in the right system is larger than log n. Now this gives you a...
Sorry, what is begin?
Begin is the number of external legs.
The number of...
Oh, external legs of the tensor network. So it's basically telling you that if you want, so you have log n, you have, suppose that you have n degrees of freedom in the bulk FT, right? That encode your all your bulk simple states, and then you want to map them to, you can encode those in a log n number of, what I mean is that if you have a dimension of the physical space that is 2 to the n in the bulk, right? And you want
That's the radiation, that's entangled. Is that what I'm supposed to think of here as the Hilbert space?
No, it's the naive bulk effect effect theory. It's the Koza space. Like the one that is bigger.
So the connection to the boundary is sufficiently big.
And the left-hand side is what connects you to the boundary.
Yeah, that's what I thought.
Yeah.
The right-hand side, this capital N is a dimension of the Koza space.
Yeah, it's basically the number of degrees of freedom that you have in the world, yes.
Well, the number, no. That's really by the left-hand side.
No, of naive bulk effective theory, degrees of freedom. It's like in the black hole integers, that then
The radiation is a naive degree of freedom, but you're using it as...
what I mean is that this, okay, in the black hole case, this is the area of the horizon, and this is, and it's like the number of possible states that you have
in your case, it's all bulk degrees of freedom. You're just... It's correct to say that capital N is the dimension of your code subspace.
Yes, and this is the...
This is just the radiation, which is not
This is
all part.
the entanglement, the degrees of freedom that entangle between the cosmology and the
It's just the radiation.
no, the part is that we estimated. No, it's not the same amount of degrees of freedom.
I thought that's basically the thermal radiation that's entangled between
Yeah.
cosmology and the
Right. Well, so what we're trying to do, maybe I should have explained better that's another model. The idea is that what we want to do is take a universe.
I completely understand.
Okay.
You don't want to give it those names when you have a completely abstract model. But I'm much more interested in the physical model. So
Right.
I'm not saying anything wrong about that. Right? When I say that capital S and capital SL and SR are the entropies of the radiation on the left and right side of the shell, whatever, on the radiation.
Right. Yeah.
And capital N is going to be the dimension of the Hilbert space that's backed by these operators that index is capital I, psi I, whatever they were called.
That's it. And the dimension, sorry, and it's the dimension of the Hilbert space that there is.
Capital N is the dimension of the code subspace.
Right, but the Koza space in some like bulk effective theory, where you take like your cosmology and you have a gas of particles in it, and you take the number of degrees of freedom to be as large as possible before collapsing that gas into a black hole.
Why are we doing that?
Because the idea is that we want to estimate how many naive bulk degrees of freedom you have, which will be smaller than the number of degrees of freedom that you are having entangled. Otherwise, the map, of course, will be isometric. If the number of degrees of freedom in the bulk is the same as the entanglement, then the map is isometric, right? Yeah. So the idea is that you could have in principle more degrees of freedom in the bulk than you have in the boundary. So you are then there is entanglement.
I just didn't understand why we have to worry about anything collapsing to a black hole here. I certainly agree that if you make the code subspace too large, then the isometry will become a non-isometry.
Right, so yeah, to model the picture of the non-isometric map that we showed before, what we're doing is take the bulk, this is what I have here, take the bulk damping legs in the cosmology and define the Koza space to be very large, to be much larger than this. And then the way we estimated this number to reach this formula is this one here, which is telling you it's the number of degrees of freedom that you can put, if you take a gas at some temperature in a box of size L, then that's the maximum number of degrees of freedom you can put there without collapsing it microcanonically into a black hole.
Okay, I think I'm going to have to ask you about that.
What?
I think I'm going to have to ask you about that later. I'm sorry.
Okay, anyway,
I'm sure
this is just an estimate of. Let's see, is there another intuitive way to look at it?
No, don't worry about it. I think we also have to finish.
Yeah, okay, and this is my last slide. And everything I want to say here is that you can have isometric encoding as long as the entanglement goes like log of the dimension of the bulk. Koza space.
That sounds familiar.
Yeah, entropy is bigger than
Right, exactly. So you have it's an expansion separation as is usual in these cases. And this transition is very fast. Like as long as you pass, you immediately get So yeah, I'll leave you with some open questions. Yeah, I'd say the most interesting one maybe is the first one, which is whether or not the Berkeley effective theory actually breaks down, which I think is something that is not that clear if you have very small entanglement between the ball and between the cosmology and the spacetimes. But yeah, I'd be happy to discuss. I mean, I'm around any of these questions. Okay, so this is all I have. I'll leave you the cosmic bets that almost made it to the paper, but were commented
Yeah, you
out.
have to show that.
Or I must do it. Let's thank Stefano.